This is a 28C programmable ROM, this is an 8-bit computer bus, and this is an Arduino Nano. Hey, I'm Trevor Makes, and I have several projects I'm working on that require burning some custom ROM chips. I decided to try out 28C series EEPROMs because even though they're more expensive than other PROMs, they don't require higher voltage sources or UV light for erasing or programming, making them much easier to interface with. In fact, they can be written over a plain computer bus, just like an SRAM chip, making them useful as a storage device, as long as some particular timings are observed. It's not so much that they're read-only, just that writing takes much longer than reading. When I looked around, I found a ton of DIY designs for 28C programmers using Arduino, but I didn't find any that I was totally happy with. The biggest challenge with using an Arduino is the limited number of I/O pins for interfacing with a computer bus. An 8 kilobyte EEPROM, for example, requires 8 data lines, 13 address lines, and a pair of read and write signals, 23 lines in total, while an Arduino Nano only has 20 I/O pins, and that drops to 18 if you plan on using the serial connection with a computer. Most designs I found seem to work around this by using serial in, parallel out shift register chips to load the address from the Arduino 1 bit at a time. While this certainly works, it's not the most efficient, and it left me wondering why nobody was using parallel latches to instead load the address from a shared data bus. This way, instead of shifting the address out bit by bit, you can write the address one whole byte at a time. Historically, this multiplexed bus design with latches was actually used by the earliest microprocessors, like the Intel 4004 and 8008, in order to fit those devices into the smallest package possible. So it seems only fitting to reuse that sort of design with a low pin count Arduino. I went with 74 HC573 8-bit latches, since their pin configuration with inputs on one side and outputs on the other is perfect for the breadboard layout that I had in mind. I've placed 2 of the latches in the upper left corner of the breadboard for 16 address bits total, making up a 64 kilobyte memory range. I tied the output enable pins to ground so the address output will always be enabled. The blue jumper wires carry the address bus all the way across the upper half of the breadboard, so any devices placed on the lower half can run jumpers vertically to tap into the bus. The order of the address lines is arbitrary, but I chose to put the most significant bit at the top and the least significant bit at the bottom. Below the address lines, I similarly placed green jumper wires to carry the data bus across the breadboard. Instead of being driven by latches, these lines will be tied directly to the Arduino's I/O pins. This way, the data bus can be configured both as an output and an input, whereas the address bus is output only because of the latches. Again, I chose to put the most significant bit at the top and the least significant bit at the bottom. Finally, the read and write enable lines cross the breadboard with yellow jumper wires, read enable above and write enable below. To load the address, the latch inputs and data lines are tied together, A15 to A7 to D7, A14 to A6 to D6, and so on, so that the upper and lower address bytes can be latched from the value written to the data bus. Now the Arduino can be wired to the data bus, which brings us to the choice of which I/O pins to use. Technically, any arbitrary arrangement of pins could work if they were set 1 bit at a time, but the whole point of using latches was to avoid the bottleneck of shifting data out serially. A much better choice is to take advantage of port I/O, which can write up to 8 pins at the same time as long as they all belong to the same port. If we take a look at the Arduino Nano's pinout diagram, we can see that there are 3 ports, with 6 pins in port B, 6 pins in port C, and 8 pins in port D. At first glance, port D seems like the obvious choice, since we could hook the 8 data lines directly up to the 8 pins of port D, and with port I/O, we could read and write a byte from the bus with a single CPU instruction. Unfortunately, the lower 2 bits of port D are shared with the hardware serial peripheral, so using all of port D would exclude the USB serial connection, and I'd really like to use that for uploading files from a computer. The next best choice is to split the data bus across 2 ports. I've opted to use the upper 4 pins of port D for the upper 4 data bits, and the lower 4 pins of port B for the lower 4 data bits. This way, the data bits are at least aligned with the port bits, so they won't require any bit shifting, but I'll go into those details a little bit later. Finally, the two latch enables, the read enable, and the write enable are all wired up to the Arduino. These are all single bits, so really any Arduino pin is fine for these. I chose the upper 4 bits of port C since they were less crowded over on the other side of the Arduino. I also added 1 kilo ohm pull-up resistors to the read and write enable lines to prevent data corruption, because the Arduino's built-in pull-ups don't work during reset or programming. With the whole computer bus wired up to the Arduino, let's get started on coding so we can check to make sure everything's wired up correctly so far. For this project, I'm using Visual Studio Code with the Platform IO plugin. First, I'll create a new folder with a platformio.ini file that looks like this, with my core library included. Now, when I open the folder with Visual Studio Code, the Platform IO plugin will configure the project and download the libraries. I'm using a newer model Arduino Nano, so I'll select that for the environment setting. Now we can add a main.cpp file and start writing code. What we need to do is drive the Arduino's I/O pins so we can control all of the wires that we laid out across the breadboard. The beginner's way to set I/O pins is with the digital write function, which is easy to use but rather slow and only works 1 bit at a time. The more advanced way is to directly write to the built-in port registers, which can drive up to 8 pins at the same time. This would look something like ddrd equals FF to configure all of port D as outputs, port D equals AA to write alternating bits to port D, or port C or equals bit 5 to set just pin C5. These will generate the most efficient code possible, just 1 or 2 CPU instructions for each of those lines of code, but it's neither flexible nor easy to read. Instead, I'm going to show off some really cool C++ type templates that I've been working on for my open source core library, which you can find at the link here. First, we need to include the core/IO header. Then use the core port macro to generate types for each I/O port B, C, and D. These define camel case types like port D and port B. Since the data bus is wired to the upper 4 bits of port D, we need to mask off just those bits, and then do the same with the lower 4 bits of port B. To join both ports into a single byte, we import the bit extend adapter and wrap it around both ports with the most significant bits on the left. Finally, to make the type easier to use, we can give it a shorthand name like data port. So far, all this has done is define a data type. No memory has been allocated and no code has been generated. But we now have access to the static functions of the data port type. The config output function configures the selected I/O pins in output mode, and the write function sets the selected I/O pins to the given data. Under the hood, the data is being masked off and sent to ports B and D as defined by the data port type. Pretty cool, right? It gets better though. Let's take a look at the assembly code that this actually compiles to. Here's an awesome website called Compiler Explorer that lets you experiment with different programming languages and compilers and lets you examine the assembly code that's actually generated. On the left, we have the Arduino code that we've written so far, and on the right, we have the generated assembly language. It's a little easier to understand what's going on if we compare the assembly with the equivalent C++ code. The first 6 lines set the upper and lower 4 bits of the direction registers to configure those pins as outputs. The next 6 lines read the lower 4 bits from port D, joins them with the upper 4 bits of data, and then writes the result back to port D. And the last 5 lines do the same thing with port B, except with the upper and lower 4 bits swapped. Notice that there's no overhead from function calls despite being generated from nested adapter types. The low-level details are abstracted behind the data port type, but we can still count on it to generate efficient code because the compiler can optimize static types during compilation, rather than relying on runtime jump tables as with dynamic polymorphism. Just for fun, let's look at what happens if we redefine data port to just port D. Now we get just 3 lines of assembly equivalent to ddrd equals FF to configure the port as output, and port D equals data to write the data to port D. This would obviously be much faster, but again, because USB serial shares 2 of those pins, and because I want to use that for transferring files, we'll just have to settle for the split data ports. Even so, the code will still be plenty fast. Okay, enough low-level stuff. Let's get back to writing code so we can actually test out the circuit. With the data port defined, the next step is to hook up the address latches. First, include the core/IO/bus header. Then import the active high, active low, latch, and word extend adapter types. The latch enable lines were wired up to pins C5 and C4 for the most significant and least significant address bytes, respectively. These use active high logic levels, meaning a high output value activates the latch. So we wrap them with the active high adapter type. Now we can use the latch adapter type to wrap data port and the corresponding latch enable. These new types can be configured and written just like data port, but they generate a couple extra instructions to set and reset the latch enable pin after writing data to the bus. Finally, the two address bytes can be extended to make a 16-bit port using the word extend adapter. The functions we've written so far will allow us to set all 3 bytes of the computer bus, but we don't have a way to call them yet. This is a perfect use for another part of my core library, the command line interface. This works just like the command prompt on a computer, but instead of running programs, it lets us call Arduino functions. First, we include the core/CLI header. Then import the streamx, CLI, command, and args types. Next, create a streamx wrapper around Arduino serial. This has the same interface as the Arduino stream type, but extends it with features like reading the arrow and delete keys, printing text with color, and moving the cursor around. In a later video, I'll show you how these features can be used to create video games like Tetris, so don't forget to subscribe if you'd like to see more. Now we can create a CLI object with streamx as the I/O source. In the setup function, we do the usual steps to initialize the serial connection. Next, in the loop function, we create an empty list of commands and pass it to the CLI's run once function. To make our functions callable from the CLI, they need to take an args parameter. Then we can call args.next to read an argument from the command line and convert it to an integer using a to I. Now we go back to the command list and add a command named data that calls the setData function. Repeat the same steps with the setLSB and setMSB function, and we're finally ready to upload the code and try it out. Now that we know the data and address lines are wired up correctly, we can start hooking up the EEPROM. I'm using an AT28C64B with 8 kilobytes of memory. The pinout has 13 address lines, 8 data lines, write enable, read enable, and chip enable. Normally, in a computer bus with multiple devices, the chip enable would be fed by an address decoder, but here I've just tied it to ground since it's the only device and will always be selected. And the rest of the pins just tap into the corresponding bus lines on the top half of the breadboard. I love breadboarding the computer bus this way because it's easy to trace wires from any chip to a label, making it simple to build and inspect, and the bus can easily be extended to make room for other devices, like a second ROM to copy data from. Pretty cool, right? If you think so too, please remember to give this video a thumbs up. I'd really appreciate it. Now that the EEPROM is wired up, we can continue working on code to read and write data from the bus. Let's start by defining types for the read enable and write enable lines, which were wired up to pins C3 and C2 respectively. These are both active low control signals, meaning they need to be pulled low to start a read or write. So we wrap them with the active low adapter type. Now we can define an interface for the computer bus using all of the types that we've defined so far. Start by inheriting a struct from the base bus type. Then implement the config write function. This should configure all of the bus lines as outputs. Next, implement the write bus function, which takes the address and data to be written as parameters. The write procedure and timings can be found in the EEPROM datasheet. First, we write the address, followed by at least 0 setup time. check. Then the write enable pulse can begin, followed by 50 nanoseconds of hold time before the address can change. It would take at least a 62.5 nanosecond CPU cycle to change the address anyway, so this will always be safe. Next, we write the data, followed by 50 nanoseconds of setup time. Again, this is less than one CPU cycle anyway, so totally safe. And finally, we end the write pulse. The 100 nanosecond minimum write pulse width is also safe because the set bit instruction that makes the pulse takes at least 125 nanoseconds anyway, so everything checks out timing-wise. Next, implement the config read function. This should configure all of the bus lines as outputs, except for the data port. The read bus function writes the address to the bus and returns the value read back. The read procedure and timings can be found in the EEPROM datasheet. The first step is to write the address. The data port needs to be configured as an output to write the address, so do that first, and then write the address. There should be at least 150 nanoseconds between the address we just wrote and when the data is ready to read, but before that, we need to start the output enable pulse. The latency between output enable and reading the data is a bit more complicated. First, the EEPROM expects 70 nanoseconds before the output is considered valid. Then the Arduino's port read latency is up to 1.5 cycles, or 94 nanoseconds. So it could take something like 164 nanoseconds or 3 CPU cycles before the data can be read. Empirically, I found 2 no-op instructions inserted between enable and read to add just enough delay. But data port config input should take at least 2 cycles, so if we put that between enable and read, it can be used to account for the latency instead. Now the bus data can be read, and finally end the output enable pulse and return the data. Now we can write a pair of command line functions to test the bus interface. First, a write bus command that takes 2 arguments, the address and the data, and then uses the bus functions we just wrote to write the data. Then do the same thing with the read bus command, take an address argument, and then print the value read back from the bus. Add the new commands to the commands list, and the code is ready to upload. With the new code uploaded, let's try writing a few bytes, and then make sure we read those same bytes back. Okay, we got the same data back, so the EEPROM appears to be working, at least for writing single bytes at a time. But to write any faster than 100 bytes per second, we'll have to carefully follow the paged mode write procedure. The paged mode write waveform adds 2 more constraints to the write timing. The first is the load cycle time. As long as consecutive writes are with 150 microseconds of each other, and they land on the same 64-byte memory page, it's just like writing to SRAM. But once a full load cycle goes by without a load, the write cycle begins and it takes up to 10 milliseconds before another load cycle can start. So in the best case, we buffer up a page of data over 10 milliseconds, and then we write it out all at once when the EEPROM is ready for another load cycle. The companion code for this project on GitHub includes a paged write adapter for the bus type that handles the page mode write timing for us. So we can freely make write bus calls, and the adapter will batch them as efficiently as page mode allows. I'm only going to show how to use paged write in this video, but if you'd like to learn how it works, be sure to check out the code at the GitHub link to learn more. Now that the bus interface is defined, we can actually import a whole library of built-in command line functions for working with memory, including copying files from a computer. These are found in the core/mon header. The command templates use a static type to define the interface with the bus and the command line. To set this up, inherit a new API from the base API type. Then add the static getStream and getCLI functions to return references to the serialX and serialCLI objects that we created earlier. Finally, define the all caps bus alias using the paged write adapter around bus. Now that the API type is defined, we can pick and choose the commands that we'd like to import. The most useful commands will be export, import, and verify, which copy Intel hex files to and from a computer. We can also import commands for directly poking at memory over the bus. Hex prints memory in hex and ASCII. Set writes a string of bytes to memory. Fill fills a range of memory with a repeating byte, and move moves a block of memory to another address. That gives us plenty of commands for moving data around, but there are still a few special escape sequences we can implement to unlock some other features of the EEPROM. The first is the full chip erase, using the sequence listed in this waveform diagram. This writes to different memory pages within the same load cycle, even though that violates the page mode timing. This is why the escape sequence has to use the plain bus type, because the paged write adapter would insert delays whenever the page changes, ensuring that the escape sequence would be written to memory verbatim. The next sequence enables software data protection, making the chip read-only. And here's the protection disable sequence to make memory writable again. Wire these commands up to the CLI, and finally we can upload the code and try out the new commands. The baud command can be found at the GitHub link. This changes the serial data rate from the default 9600 to the faster 115200, which can send an 8K ROM in just a few seconds. I'm going to flash this ROM as a Commodore 64 dead test cartridge, which I found in raw binary format. Also included at the GitHub link is my bin to IHX Python script, which converts the data to Intel hex format. This makes a plain text file that we can copy and paste into the serial monitor after typing the import command. Then type the verify command and paste to make sure it reads back the same values. Finally, type the lock command, and the data should now be protected against accidental writes. Now I can pop out the ROM and socket this Commodore 64 cartridge adapter. But if you want to see what I do next with the Commodore 64, you'll have to check out this video over here. And if you want to keep following along as I build more projects like this, click over here to subscribe. Thank you for watching.